In this lecture, we're going to continue with IP addresses, and we will look at the actual IP addresses, what they're made of, subnets, and some of the protocols we use on them. And we start that off with IPv4 addresses. They are made out of 4 octets, and that is also called a dotted decimal notation. We can then break each of those numbers, each of the 4 octets, into the 8 bits they're comprised of, because data really is just zeros and ones. And we do this because it's easier for us to read. For this exam, you don't really need to dive too deeply into IP addresses and subnets, but you need that basic understanding of how it works and where we use it. And the reason we have the dotted decimal notation, like I mentioned, it is much easier for us to say 172.16.254.1 than it would be to say the binary, just 172.10101100, and that's just 172. So we made up dotted decimal notation because working with just the binary will become cumbersome and annoying. Over here on the right, you can see that address I talked about broken into binary. Each of the numbers have their binary 8-bit number assigned. The last bit is a 1, the second 2, the third 4, the fourth 8, and you can see here it just doubles every time. So here, if you wanted to write the number 1, you would get 7 zeros and then a 1. If you wanted to write the number 2, you would get 6 zeros, then a 1, and then a 0 again. And just for simplicity, I have a math calculation here at the bottom, and this is just for the first 172. You take 172 minus 128. That is the first bit. That indicates 128. You take 172 minus 128, you have 44 left. Since the second bit is 64, that is bigger than 44, we don't do anything on the second bit, that is a 0. The third bit, 44, is bigger than 32, it is a 1, that leaves us with 12. 16 is bigger than 12, that bit is a 0. On the fifth bit, 8 is smaller than 12, we minus that leaves us with 4. The sixth bit, 4 minus 4, that leaves us with 0. And on the 7th and 8th bit, they're both zeros because we don't have anything left. So the binary value of 172 is 10101100. And no, you probably won't get math subnetting questions on the exam, or at least not very complex ones. But you may get something saying, is this a public or private IP? Or this is the IP we have, which subnet is that in? So this is another one of those areas where if you just know this stone cold, you can score some easy points. And just like we use the dotted decimal so it's much easier for us to read than the 32-bit integer, we do something similar for websites. It is much easier to remember google.com or thorteachers.com than it would be to remember 66.102.12.231 or even worse, the IPv6 version of that. You just go into your browser, you type in google.com, and then your computer goes out and asks, what is the actual address of this website? And depending on if you use IPv6 or IPv4, you get one of those replies back, or any of the multitude of IP addresses that Google uses. Here again, of course, we do everything that we can to make the experience as seamless as possible for the end user, and they don't see all the technical stuff that's happening behind the scenes. As you probably remember, IPv4 was never built for what we use it for today. It was an insane amount of IPs that we would never run out of, but we did. And when we started seeing the signs that we might at some point run out, we divided IP addresses into public addresses. Those are the ones that can be routed over the internet, and we use those to communicate with hosts over the internet. That's internet routers, websites, anything that has to be publicly available. And then on top of that, we made private addresses. And private addresses is what we use on our internal networks. If you recall the socket pair I had earlier, where my address was 192.68 something, that is my private address. And my internet-facing router would have a public address. That is where all the traffic outbound and inbound goes through, and any device I have behind the router, that has a private address. And it makes sense that we did this because millions, if not billions, of the IPs we were using were devices on a local network. If all of those start using private addresses, well then we can use the public addresses for everything that needs it. For private IP addresses, we have three ranges. The entire 10 network, all the way from 10.0.0.0 to 10.255.255.255. That will give an organization 16.7 million usable IP addresses, which could be useful if you have a very, very large organization and you segment logically your network into different departments in different devices. The second range is 172.16.0.0 to 172.31.255.255. That range gives you slightly over a million IP addresses. And then finally, the last range, 192.168.0.0 to 192.168.255.255. That gives you just about 65,000 IP addresses. Almost everything else outside of those ranges are public IPs, and those are the ones that we route over the internet. There are, however, a few exceptions. One of those exceptions is the entire space for 127.0.0.0. That is used for loopback IPs, and that will be on your PC only. And if you look over here on the right where I have the 127 network written out, you can see it says /8. And that is the slash notation or the CIDR notation, and we will cover that in a couple of slides. If you know a little bit about networking, then you know /8 means that is the entire 127 network, from 127.0.0.0 to 127.255.255.255. The other two notable IP spaces is 169.254.0.0/16, and anything in the last two octets, those are the ones that here are .0.0. Those numbers can really be anything. It doesn't matter what they are. And if you see that 169.254 as your IP address, then something is wrong. That means there's a communication problem and you're not getting the IP that you have requested. And then finally, we have the broadcast address for IP. We already talked about that one, 255, 255, 255, 255. When we realized we were running out of IP addresses other than the public and private addresses, we added another Band-Aid solution. That was NAT and PAT, Network Address Translation and Port Address Translation. So let's cover static and pool NAT and PAT. First off, we have static NAT. That means that it is static translation between the internal and the external address. So for every private IP we have, if that IP needs to access the internet, well then it needs a public IP as well. Now at the time when we used this, not everything needed to get online. So we did save some IPs, but not a huge amount, which is why we made PoolNAT. That was a small improvement. That just means that the amount of IPs that needs to access the internet at the same time needs a public IP. If 25% of our team needs to be online at any time, well then we need 25% of our internal IPs as public IPs. The problem here is if 27% needs to get online and we have 25%, well then the last 2% cannot get online. It is still a one-to-one translation, but only for the ones that needs it, which is why we designed the next one, which is PAT. And that is what you saw in my output from earlier. PAT uses the IP address and then the port number. It is also called one-to-many PAT or NAT overload since it translates one public IP into many private IPs. And this is what we use mostly today if we use IPv4. So remember, NAT is one-to-one, it is static, you have to have one public IP for each private IP that needs to get online. Pool is a little more flexible, you have a pool of addresses, but once that pool is used up, no one else can get online. And then finally, we have PAT, that is what we use today, one-to-many, and that is probably the extent you need for the exam. Early on, when we used IPv4 addresses, organizations would use classful IP networks, which means that every network has over 16 million IP addresses, even if they just need 5 or 10. Obviously, a very, very inefficient way of using IP addresses, and when they realized that would be a problem, they designed classless IP networks. And that is the slash or CIDR notation I mentioned earlier. And CIDR just means classless interdomain routing. And we use it to break larger ranges of IPs into smaller logical segments. First off, we save a ton of addresses. Secondly, it allows us to divide our network into the sizes that we want. We, for instance, wouldn't want payroll, human resources, and accounting to be on the same network and to be able to access the same files. We logically segment them out on their own network, and depending on the CIDR or slash notation, you know exactly how many IP addresses are in that subnet. If you know subnetting, you know CIDR notation, you know the address I had earlier, 172.16.254.1/24, then you know just from those numbers how many IP addresses are in that range and what the broadcast address is. A /24 network is by far the most commonly used notation, and it has 256 addresses. 255 of those can be used for hosts. If you're new to networking, the CIDR notation or the slash notation might seem counterintuitive. The higher the number is, the less hosts we're going to have. If we're designing a network and we can tell we will never use the 256 addresses, we might need 10. Well, then we use a higher CIDR notation and we make that smaller network just for that segment. But I would probably be a little expansive when I assign IP addresses and assign a bigger range. Even if we don't need more than 10 addresses today or tomorrow or in a week, I still probably wouldn't do a /28 where you have 16 addresses. Because what if something changed? What if in 2 years that team expands tremendously? So for this, maybe I would do a /27 or 26 where they would have 32 or 64 addresses. Remember, minus 1 for the host, that means 31 or 63 addresses that are usable. So in 2 years, when that department grows, we can easily add 20 more systems. And we don't have to redesign our network and allocate IPs again. Earlier on, when we had, let's say, a /24 network, the first and the last address we would never use. That would be the host address and the broadcast address. Now, we only have the 255 address that we don't use since that is the broadcast address. Now let's finish out IPv4 with looking at the headers. If you remember back to when we covered the OSI or the TCP/IP model, I talked about how headers were added to each layer of the network. So this is how an IPv4 header looks. And remember, IPs are layer 3 on the OSI model. And this is all the information that is in the header. This is not the actual data. It will have a version number. Since this is IPv4, it is version 4. It will have information on how long the header is, if we're using quality of service or not. Remember, that's the one where certain traffic gets priority, most often stuff that is real time. Then we have a bunch of identifications, flags, and offsets, a packet number, assuming this is TCP. Then it will have the protocol, TCP or UDP. Then it will have the source and destination IP, and we can add some additional options and some padding. I would also be familiar with the term TTL or time to live. Each package, when we send it over a network, it has a certain amount of hops that it can go, and each router decrements that with 1. And we use the time to live to prevent router loops. Let's say we have 3 routers that are connected to each other, full mesh, A, B, C, D. Router A thinks it needs to send the package to router B thinks it needs to send it to C thinks it needs to send it to A, and so on. That traffic is going to go in a circle. It's just going to continue round and round, eating up bandwidth. So to prevent that, we have time to live. Every time that packet passes through a router, it removes 1 from the time to live. If on router A it is 15, then on B it would be 14, C 13, and so on. At some point, it is going to hit 0 and the package will be dropped. We have prevented a routing loop. And then finally, we have MTU, Maximum Transmission Unit. It is normally 1500 bytes for Ethernet usage, and if a package is bigger than that, then the router might choose to break it into smaller fragments so that one package doesn't exceed the size that it should be. And with that, we are done with IPv4. I will see you in the next lecture where we cover IPv6.